As far as differential equations goes, in chapter 1, we started off with scalar differential equations, scalar ODEs, first order, involving first derivatives, including our favorite scalar ODE, dy dt equals, say, little a times y, with, say, an arbitrary initial condition, y of 0 equals y sub 0, or y naught, as we called it, having unique solution, y equals, okay, we can use the phi notation, phi sub y naught of t equals y naught e to the at. That would be the more typical way to write it as a scalar function. Although if we were trying to make the analogy with the vector form and the beautiful generalization, we'd put the a to the at first, and in fact, we'd even put the t in front of the a and put the y naught second. Of course, it's the exact same thing, just written in kind of a weird way for a scalar function, but that makes the analogy with the vector case, right? If a were a matrix and y naught were a vector. It's completely analogous. That's what I call the beautiful generalization. You can solve this by guessing. You also could solve by separation of variables. You should know how to separate variables. There was at least one question on the first exam about separating variables. We haven't done that in a long time, but it's a basic skill you should be able to do to solve some basic differential equations. In the very first 4 sections of chapter 1, we also talked about qualitative approaches. First of all, that was slope fields. And not just for autonomous equations, but non-autonomous, if the right-hand side involves time as well. Non-autonomous equations, you can make slope fields for non-autonomous equations as well. They're harder to make, but you can make them, or you can have the computer make it, and you should be able to sketch in solution curves to follow the slope field. And a numerical method, Euler's method, for approximating solutions with discrete points based on a step size delta t and a number of steps. I'm not going to have the time to remind you of every formula here. You should know the formula for Euler's method. Then we got into existence and uniqueness, theorems. If your right-hand side function is continuous as a function of t and y, or if it just was, if it were autonomous, it would just be a function of y, then solutions will definitely exist. If in addition, the partial derivative of this with respect to y is also continuous, then solutions will be unique. Existence makes us happy because we're not studying nothing, right? It's important. We're not studying nothing. We're studying things that exist. Uniqueness makes us even more happy because then with uniqueness in the slope field, distinct solution curves do not touch each other, which is sometimes helpful in saying solution curves for initial value problems have to stay between 2 known solutions, like 2 equilibrium solutions or something, even if the equation itself is really complicated. It's got some practical applications. Then we got into phase lines. For autonomous equations, when you got an autonomous differential equation, the slope field only depends on y, meaning the slope marks are constant along horizontal lines where y is constant. It doesn't matter what t is. And so if you can find roots of f of y, those are going to be equilibrium solutions. And where f of y is positive, solutions increase, and where it's negative, solutions decrease. So effectively, we can collapse all the information in the slope field onto a vertical line. The equilibrium solutions become equilibrium points. That can be sinks or sources or nodes. That can also be told by linearization, looking at the derivative of the right-hand side function. If it's positive at an equilibrium point where it crosses the axis, then on the phase line, that equilibrium point's a source. And if it's negative, the equilibrium point's a sink. It's analogous in the linear system case, and also nonlinear systems with the Jacobian matrix, to having positive eigenvalues versus negative eigenvalues, or positive real part versus negative real part when you've got complex eigenvalues. The eigenvalues are of the Jacobian matrix are kind of like the value of the derivative in the one-dimensional case. So we have phase lines, equilibrium points, sinks, sources, nodes. Linearization is the one-dimensional version of the Hartman-Grobman theorem. Later on in chapter 1, we got into more methods for solving. There's undetermined coefficients, and integrating factors. IF stands for integrating factors. For what? For first order linear equations of the form, in general, A of t times y plus b of t on the right-hand side. dy dt equals A of t times y times plus b of t. A of t and b of t don't have to be linear functions. The reason this is a linear equation is because it's linear in dy dt and y. Neither of those things is being squared or cubed or square rooted, right? It's a plain dy dt and a plain y. That's why this is a linear differential equation. With the undetermined coefficient approach, you consider the corresponding homogeneous equation where b of t is 0. Find yh by separation of variables, perhaps, or guessing in simpler cases. And then you, for the non-homogeneous equation, you write it in the linear operator form. Say subtract A of t times y from both sides and say, okay, based on the form of b of t, what should I guess for yp? And then this is also a good form for the integrating factor form, a method, because the integrating factor mu of t ends up being e to the integral of whatever this function is, dt. You multiply both sides by the integrating factor, you integrate both sides, the left-hand side becomes easy to integrate, and you can still ultimately solve for y. I did miss something here. I missed also bifurcations was in here in the one-dimensional case. And that essentially is chapter 1. Bifurcations was missing. That was section 1.7. Chapter 1 for differential equations. What were we doing with linear algebra at the same time? Initially, we were keeping it really simple. We were talking about coordinate systems. Coordinates. From an intuitive standpoint, I mean, there's your ordinary rectangular coordinate systems that you're used to since, I don't know what, 7th, 8th grade, but also skewed coordinates from an intuitive perspective. Later on, we got more advanced with coordinate systems. Talking about points and we also talked about the basics of vectors in the plane as arrows and having components. You know, if that distance right there is A and this is B, and it's a vector that truly points to the northeast like this, A and B, think of those as, in general, sign distances. They're going to be positive for this picture. The vector V is a linear combination of I hat and J hat. You can write it like that. We are more used to writing them as column vectors, so we would write them like this as well, ultimately for the purpose of matrix multiplication. Dot products and projection vectors, projections. Also in here, we started working in the basics of systems of linear equations. If you've got a system of 2 linear equations and 2 unknowns, you can solve it either by substitution or elimination, either way pretty quickly. The basic geometric interpretation of that is one equation gives you one line, another equation gives you another line, and the solution is the point of intersection. That's the, the basic, most basic geometric interpretation, not talking about linear transformations yet, though we quickly got into linear transformations. I'll just write LTs. Initially, purely geometrically, you remember that? Talking about rotations and reflections and that kind of stuff. But in general, linear transformations are defined by, well, in the two-dimensional case, at least, systems of equations. Say u equals ax plus by and v equals cx plus dy. That's the two-dimensional case of a transformation from R2 to itself. Then we generalize that ultimately to transformations from, say, Rn to Rm, defined by matrix multiplication. Such a transformation, if it's linear from Rn to Rm, n-dimensional space to m-dimensional space, is going to have a matrix A that's going to be m by n. Got to switch around the n and the m rows and n columns. The formula for t is going to be t of x equals a times x, where x is in Rn, right? A has m rows and n columns. It's got to match the number of columns of x as a column vector. The result, a times x, is a vector in Rm. There's ideas about being one-to-one and or onto. Related ideas of kernel of T, which is the null space of A, and the image of T, which is the column space of A. You could talk about the kernel and image of a transformation that's nonlinear as well. Kernel and image are more generalized ideas than null space and column space. If T were a nonlinear transformation, the kernel still could be defined to be the set of all inputs that get mapped to 0. And the image can still be defined to be the set of all outputs of the function, even if T were nonlinear. But if T is linear, meaning it's also operation preserving, OP, operation preserving, then there's going to be a matrix A that gives you the formula for T of x as A times x. The null space of the matrix is the set of x's such that AX is 0, same as the kernel of the transformation. And the column space of the matrix is the set of all linear combinations of the columns of A, same as the image of the transformation, because, it's very important, because of how we define matrix multiplication. AX being a linear combination of the columns of A with the entries of X as the weights. This is a definition. And that's an important definition to know, okay? It helps you understand a lot of things. In particular, one thing it helps you understand is why the column space of A is the same as the image of T. Because the column space of A, by definition, is the set of all linear combinations of the columns of A. And when we do T of x as A times x, we are getting a linear combination of the columns of A. That's why these things are the same. I think that's still matched all chapter 1 of the differential equations. Anything else? I think, yeah, we got into things like, well, there's the, of course, there's the row operations to REF, identifying free variables and pivot positions. It's going to be 1-to-1 if there's a pivot in every column, no free variables. It's going to be onto if there's a pivot in every row, talking about the transformation. Also talked about matrix multiplication in general, lots of linear algebra stuff. A times B, where A is, say, m by n, and B, well, the number of columns of B has to match the number of rows of B has to match the number of columns of A. And the result, the entire thing is going to be m by P. And that does correspond to a composition of linear transformations. You want to define A times B so that effectively you are composing linear transformations. Actually, so if we work from right to left here, B is going to get applied first. So since B is n times P, the first transformation is going to be from Rp to Rn. And then the second transformation is going to be from Rn to Rm. You know, whatever you want to call these transformations, S and T or something. A times B times X is going to be the same. Oops, let's write that somewhere else. A times B times X is going to be the same as T of S of X. Matrix multiplication is defined so that it matches function composition for linear transformations. Also talked about invertible matrices. You know, when does A inverse exist? Well, A does have to be a square matrix, first of all. There's the matrix inversion algorithm. You could say the inverses are going to exist if in the matrix inversion algorithm it works. When you create your big augmented matrix like this and do your row operations, you get something, you get I in the first half, and whatever's over here is going to be the inverse matrix. Of course, in the 2x2 case, there's the shortcut formula. That's nice. And that hints at the idea of a determinant and the matrix being invertible, a square matrix being invertible if and only if its determinant is non-zero. So there are lots of things here. They came up in natural ways, I think. We built them up. When we got into chapter 2 of the differential equations, the linear algebra, that's about when the linear algebra got more abstract with vector spaces and stuff. But with the differential equations in chapter 2, we were still considering nonlinear equations, but now they were systems. So we started talking about systems of ODEs, including the nonlinear case, written in vector form. And in general, it could be a time-dependent vector field, f of ty. So imagine a vector field like you would make with Mathematica with vector plot, where the arrows are changing over time. That could happen. You could consider such systems. And in fact, I think I did a little bit. Mostly we thought about the autonomous case, where the vectors in the vector field are static. Yeah, there's the autonomous case. Was the most common thing for us to think about. That's the vector field there. The idea of a vector field is somewhat similar to the idea of a slope field, except solutions in the phase plane, they don't have to pass the vertical line test because they're not graphs of functions. In the ordinary sense, they're graphs of parametric curves. So you can have vectors that are, for example, rotating, so to speak, and solutions that like rotate, that follow that vector field. And it's not a problem that it fails the vertical line test. You're not even thinking about the vertical line test here. That's a parametric curve. So capital Y of t equals, if you write it as a point, you could write it this way. You could also write it as a column vector. It's not a big deal either way. We're mostly actually used to writing them as column vectors, but you could think of them as being a point. This is a Y here, by the way. I could use the phi of t notation here as well. But all the stuff we did in chapter 1 still applies as far as qualitative approaches, numerical approaches, Euler's method still comes back up into play. There's also existence and uniqueness theorems again. And most importantly, with autonomous equations, distinct solution curves can't touch in the phase plane. With non-autonomous, they actually could, because the true phase space for a non-autonomous equation includes another dimension for t. And in that third dimension, solution curves don't touch. But we never really considered that much. I did a lot of extra stuff that is not in the book here at this point with flows. The key property being the flow property that when you compose two flows like this, where y naught is your initial condition, you can add the numbers s and t. That was most relevant for us with linear systems in chapter 3. I'll come back to that. But it is still true that this works for nonlinear systems as long as your differential equation is autonomous. It doesn't work like this with non-autonomous equations. And there were some extra readings about that. This comes up, by the way, in lecture 35 and talking about something called stability. Doing some pretty advanced ideas with stability is dependent on the flow idea again. Okay, lecture 35, which you should have maybe watched last night or today. That was basically it for chapter 2 with the differential equations book. What were we doing about this time with linear algebra? We got more abstract. Vector spaces, subspaces, general linear transformations in such a situation. Examples are still helpful here. Certainly Rn is a vector space, and subspaces of Rn can be interpreted geometrically. If n is 3, say as, well, either just the origin, that's called the trivial subspace, or a line through the origin, that would be a one-dimensional subspace, or a plane through the origin, that would be a two-dimensional subspace, or all of R3 is a subspace of itself, and then you imagine higher dimensional versions of these things that you can't literally visualize. But it's also important to think about other examples, like spaces of polynomials. Pn is the space of all polynomials of degree less than or equal to n. And CAB is the space of all real valued functions which are continuous. The C stands for continuous on the closed interval from A to B. It doesn't have to be just a closed interval. It could be the entire real number line. Functions, real valued functions with real outputs that are continuous on the entire real number line is what this represents. The elements of these vector spaces are functions. Linear transformations on such a space or such a space include like taking the derivative, although with the derivative you'd want this space as well, C1R. That stands for the space of all functions that are not just continuous on all of R, but also have a continuous derivative. It's called continuously differentiable. Heard that phrase before. And the derivative operator, for example, which you could write like this if you like, ddx as a mapping from C1R to CR is a linear transformation. Why? Because it's operation preserving. ddx of alpha f of x plus beta g of x is alpha f prime of x plus beta g prime of x. In other words, it's alpha times the derivative with respect to x of f of x plus beta times the derivative with respect to x of g of x. I didn't have to write both of those lines, but I did just to emphasize both notations are okay. This is emphasizing ddx as a linear operator is in fact a linear transformation. It is operation preserving. And if you can restrict yourself to finite dimensional subspaces of these things, like spaces of polynomials, like on the exam with the extra credit, you can even have a matrix for ddx. Right, that was the extra credit on exam, what was it, exam 3 or something? With these infinite dimensional spaces, you don't want a matrix because it would have to be an infinite matrix, an infinity by infinity matrix or something like that. So these are not finite dimensional spaces, though they've got finite dimensional subspaces. And that brings up also the ideas of span, linear independence, basis, and dimension as big ideas in that part of linear algebra. These are all connected to each other. What's the span of a set of vectors? In the abstract, it's just the set of all linear combinations of them, whether those vectors are ordinary vectors or whether they're functions or something else that you can't even imagine. Pure abstract objects. What does linear independence mean? It means that if you've got a linear combination of vectors, these are abstract vectors. These v's could be functions, but I'm writing them as if they're ordinary vectors, equals the zero vector. Linear independence means that all the c's are zero. It's analogous to the kernel of a linear transformation being trivial. Linear dependence would mean there exists some non-zero c's making this equation true. That would be linear dependence. Easiest to think about linear independence if you've got just one or two vectors. One vector by itself is a linearly independent set if it's not the zero vector. Done. The zero vector by itself is linearly dependent. Two vectors, two non-zero vectors, are linearly independent if and only if they're not scalar multiples of each other. If they are scalar multiples, then they're linearly dependent. Or if the zero vector is one of them, then it's a linearly dependent set. Once you get to three and more vectors, then it gets harder. You got to think about the more general definition. Though in R3, for example, if you had three vectors that were all on the same plane, then they would be a linearly dependent set of vectors. Would be one way to visualize that. If your set of vectors both spans whatever subspace you're talking about and is linearly independent, then it's a basis for that subspace. And if a subspace has a finite basis, then any basis will have the same number of vectors in it, and that's called the dimension of the subspace. The number of elements in any basis, assuming it's got a finite basis. You got to prove that the number of elements in any basis is the same. The trivial subspace, just zero, doesn't have a basis. And by default, that means it's zero dimensional. Lines to the origin have a basis with one vector. Any non-zero vector on that line will be a basis for that line. Planes through the origin are two-dimensional. They're going to have two vectors as a basis. Any non-zero vectors that don't point in the same direction in a plane will be a basis for that plane. In three dimensions, any three vectors that are not all in the same plane and none of them are the zero vector will be a basis. Not remembering exactly where we started to transition there with the linear algebra into the chapter 3 for the differential equations. The chapter 3 is all about linear systems of differential equations. dy dt equals a times y. The textbook approach is with eigenvalues and eigenvectors, and mostly focuses on the two-dimensional case, except at the very end. And what you want is you want to first find the eigenvalues by solving the characteristic polynomial determinant of a minus lambda I equals 0. The roots of that are the eigenvalues. By the way, I forgot to mention this, but you could also switch around the a and the lambda I. You could say the characteristic polynomial is the determinant of lambda I minus a. Instead, it does in general multiply this characteristic polynomial by -1, but it's got the same solutions. The simplest case in the 2x2 situation is when you've got two distinct real eigenvalues. And in that situation, your two corresponding eigenvectors will be linearly independent. And your general solution will be k1 e to the lambda 1t v1 plus k2 e to the lambda 2t v2, where in writing that I'm assuming v1's an eigenvector for lambda 1 and v2's an eigenvector for lambda 2. In writing this, I'm also assuming lambda 1 and lambda 2 are real numbers that are distinct real numbers. One of them could be 0. You can have 0 as an eigenvalue, but you can't have it as an eigenvector. Right, with eigenvalue, you should also remind you, you're also looking for in thinking about eigenvalues and eigenvectors, you're looking for non-zero solutions for V. This is motivated by trying to find straight line solutions, because we see that in phase planes for linear systems quite often. Straight line solutions where solutions are going straight toward the origin or straight away. And what that means is the vector field A times V is parallel to the input vector, lambda times V. That's how to interpret this geometrically. E to the lambda t times V is a solution if V is an eigenvector with eigenvalue lambda. And then forming arbitrary linear combinations of them will span the solution space. These two vectors will be a basis for the solution space. It's a function space in this case, though we're visualizing the solutions as parametric curves still. There's also the complex eigenvalue case. And there you have to write down a complex solution. I'll go ahead and write the eigenvalue as a complex number, A plus IB, say, times T, times a complex eigenvector. This is complex. And you've got to use ultimately Euler's identity to help you expand this. That's cosine BT plus I sine BT. And you only need to do this with one of the eigenvalues. You don't have to do it for the other. You end up getting, in the end, some real function YRE of t plus I times some real function YIM of t. And those turn out to be linearly independent solutions of the original equation. So your general solution is y equals k1 YRE plus k2 YIM, and there's no more i's left, right? And YRE and YIM both involve not only possibly exponential growth or decay, but also cosines and sines because of Euler's identity right there. By the way, all along in here, I forgot to emphasize, both in chapters 2 and chapter 3, there's an emphasis also on harmonic oscillators. In chapter 2, there's the emphasis of, okay, we can take a second order equation and convert it to a first order system. We still do that in chapter 3, but we also try to classify the harmonic oscillators as undamped, underdamped, critically damped, and overdamped based on the eigenvalues of the corresponding system. There was also the special case of repeated eigenvalues, and that's where Jordan canonical form comes into play. Jordan form. You know, I won't ask you as long a question about Jordan form as the take-home exam question from exam 4, but maybe a true, well, I guess there was a multiple choice question in the last exam that could show up again, just knowing what a Jordan form is. We also had trace determinant plane and bifurcations in there. And we also did a few examples of 3D systems. With the linear algebra, yeah, we were still talking more about the abstract ideas, but we also tried to apply it to difference equations. Yn equals a yn minus 1. This thing here for the differential equations is a function of t. For the difference equation, it's a function of n, and use a subscript. Instead of using e, you use lambda itself to the n power times v1, like this, for your general solution. You should be able to solve initial value problems as well in the differential equation case, you should be able to draw phase planes. And then, probably most importantly in all this, we started relating this to coordinate changes, right? I did forget to mention coordinate vectors up here. Coordinate vectors. When you write this kind of thing with respect to some basis, B, there was that strange notation there to emphasize that there are column vectors is the reason why we use that notation. But down here, we started using coordinate changes and we didn't bother with the coordinate vector notation. We had to change a coordinates matrix P. If capital Y is the original variable and capital U is the new variable, you can write Y as P times U, which is equivalent when P is invertible to U equals P inverse times Y. And dy dt equals AY, for example, is equivalent by the coordinate change to du dt equals P du, excuse me, where you hope D is the diagonal matrix. It's not always a diagonal matrix. It depends on the situation. If you've got distinct real eigenvalues, it will be. What is D? D is P inverse AP. That's diagonalization, which is equivalent to A equals P D P inverse. That allows you to find formulas for the solution in both the differential equations and the difference equation case, using for the differential equation also the matrix exponential, and for the difference equation, matrix powers. I did introduce matrix exponential earlier as well, back in chapter 2, as an extra thing I did besides flows. So ultimately, you've got the fact that the solution can be written of the original system for the differential equation, say, with arbitrary initial condition y of 0 equals y naught. We can use the phi notation like this to emphasize it's a function of t. The beautiful generalization says this is e to the ta times y naught. But diagonalization says that's the same as, this takes proof, p e to the td times p inverse times y naught. And the reason that's good is because this is easier to compute. By the way, I'll remind you P, I forgot to remind you P, the columns of P are the eigenvectors. And when there are n linearly independent eigenvectors, P will be invertible, and you can do all this. This is easier to compute than this thing directly. It's an indirect computation, you might say, of it. For difference equations, you write it as yn equals a to the n power times y naught. And that turns out to be p d to the n power times p inverse times y naught. That's also easier to compute than that directly. The flow idea still comes into play. We could give this, think about this differently. We could think of it as, say, cursive phi superscript t of y naught. Think of t as fixed and y naught as the variable. It then becomes a linear transformation. You can think about areas of images if you like. It's just kind of a fun thing to do. The most important thing that does, though, for us is it connects these two things in the sense that for integer values of t, phi sub y naught of n ends up matching y sub n for the difference equation, where the original difference equation is yn equals a times yn minus 1. Oh, no, to connect the two when you're talking about differential equations, it's a different one. It's yn equals the matrix exponential, e to the a times yn minus 1. Ultimately, in the end, if you iterate this, it ends up equaling e to the n a, y naught. And that is the same as this thing, which is the same as this thing, which is the time one map iterated with itself n times. Okay, that was probably more complicated than I should have bothered with. This is the more important stuff. Okay. Oh, it's taking a while. I need to go quickly with chapters 4 and 5 so we can get to chapter 6. So chapter 4 was forced harmonic oscillators. Second order equations, they're forced. It's simplest when the right-hand side is like an exponential function. But more importantly, when it was a cosine or a sine of some angular frequency omega. So it's like cosine of omega t or sine of omega t. There's the complex approach in trying to find ultimately the amplitude and phase of the forced response. Let me just leave it at that. Chapter 5, we got into nonlinear systems more fully talking about null-clines. We introduced null-clines much earlier than this. Linearization with the Jacobian matrix. Then special kinds of systems, Hamiltonian and gradient systems. Along the way, we tried to do some complicated problems that involved bifurcations. And in the lectures, there's extra content like linearization is essentially the Hartman-Grobman theorem. And what I'll talk about here in a few minutes, there's idea of stability as well. And then finally into chapter 6 on Laplace transforms, which I'll talk about in more depth here in a minute. With the linear algebra, we started getting into things like inner product spaces, inner products and inner product spaces. We had talked about also with ordinary vectors, things like the orthogonality. Let me put that under the inner product stuff. Orthogonality with respect to ordinary dot products and orthogonal projections. Best approximations, things like that. But that generalizes to inner products, the Graham-Schmidt process as well. Ultimately, as we've been talking about recently, for the purpose of Fourier polynomials, which are useful for approximating functions and ultimately most useful for us with regard to partial differential equations.